Let us look at proposition number 4 of works of Archimedes, specifically from on the conoids and spheroids. The proposition says the area of any ellipse is to that of the auxiliary circle as the minor axis is to the major. Given an ellipse A, B, A prime, B prime, such that A prime is a major axis and BB prime is a minor axis, and center is C. Draw the auxiliary circle on A prime. Extend BB prime to BB prime, lowercase. So let's extend them. Draw a circle O such that the area of the circle A lowercase b A prime lowercase b prime is to the circle O equal to AC is to BC. So we have to draw a circle O which has the same ratio with the auxiliary circle as AC has to BC. Area of the ellipse is equal to the area of the circle O. We draw this circle based on this proportionality, then the area of the ellipse will be equal to the area of the circle. Now let's prove this. Assuming it is not, then circle is either greater or less than the ellipse, circle O. So let's take it one by one. Let's assume that circle O is greater than the ellipse. Inscribe in the circle O an equilateral polygon of foreign sides such that its area is greater than that of the ellipse. That is, area of the polygon is greater than that of the ellipse. So basically we start off with 4-sided polygon. We increase it to 8-sided and we keep increasing the number of sides till this condition is satisfied. Inscribe in the auxiliary circle of the ellipse the polygon similar to that inscribed in O. That means same number of sides. Let this be E, F, G, H. Let P prime be the area of the polygon in the auxiliary circle. Let perpendiculars be drawn from lowercase e, f, g, h on A prime, meeting the ellipse at capital letters E, F, G, H. And let's mark the points on the major axis. And now let's mark the intersection of the ellipse with these perpendicular lines. Capital E, capital F, capital G, capital H. Join AE, EF, FB, GH, and so on, which forms a polygon P inscribed in the ellipse. EM is to caps EM is equal to FN is to caps FN is equal to GR is to caps GR. HS is to caps HS. All of these ratios are equal to lowercase bc is to caps BC, which means triangle EAM is to triangle EAM is equal to BC is to caps BC. Similarly, triangle HA prime S is to caps HA prime S is equal to BC is to BC. Trapezium EMNF is to trapezium caps EMNF is equal to BC is to caps BC. Again, trapezium EMNF is to trapezium FNCB is equal to BC is to caps BC. Again and again. Or we can say that they are all equal to the ratio lower case BC equal to AC. Instead of that, we can say caps AC is to caps BC. Why? Because remember, in the auxiliary circle, lowercase bc and AC are both radius. So that means they are equal to each other. Now, the same thing would apply in case of the triangles and trapeziums below AA prime. That means if we add up all these areas, we get the complete polygons P prime and P having the same ratio as AC is to BC. P prime is to polygon inscribed in circle O is equal to the auxiliary circle is to circle O. How? Because remember, we inscribed in the auxiliary circle of the ellipse the polygon P prime similar to that inscribed in O. So P prime is to polygon inscribed in circle O is equal to AC is to BC. Now, since P prime is to P is equal to AC is to BC, and P prime is to polygon inscribed in circle O is equal to AC is to BC, that means P prime is to P is equal to P prime is to polygon inscribed in circle O. And since both P and polygon inscribed in circle O have the same ratio with P prime, that means P is equal to the polygon inscribed in O, which is an impossibility since O is supposed to be greater than ellipse. So we can't have a polygon inscribed in the ellipse equal to the polygon inscribed in O. So that was case 1. So we have proved that circle O cannot be greater than ellipse. Now let's take the second case. Let's assume that circle O is less than the ellipse, area of the ellipse. Inscribe a polygon P in the ellipse with 4n equal sides such that P is greater than O. So here we are first inscribing a polygon in the ellipse. Let the perpendiculars from the angular points on the axis A prime be produced to meet the auxiliary circle, and let the corresponding polygon P prime in the circle be formed. Which circle? The auxiliary circle. Now, inscribe in O a polygon similar to P prime. Following the same logic, we will end up with P prime is to P is equal to AC is to BC. P prime is to P is equal to circle, that is the auxiliary circle is to O. So P prime is to P is equal to P prime is to polygon inscribed in O. P is equal to polygon inscribed in O because P and polygon inscribed in O have the same ratio with P prime. But that again is an impossibility. P cannot be equal to the polygon inscribed in O. Why? Because we inscribed the polygon P in the ellipse with 4n equal sides such that P is greater than O. But here we are ending up with P is equal to polygon inscribed in O. So since that is an impossibility, we can say O is neither greater nor less than the ellipse, which implies O is equal to the ellipse, that is in area. So which means ellipse is to auxiliary circle is equal to BC is to lowercase bc, and lowercase bc is equal to AC. So ellipse is to auxiliary circle as BC is to AC. But this BC and AC are half of the major and minor axis. So we can say ellipse is to auxiliary circle is to 2 times BC is to 2 times AC. Or in other words, ellipse is to auxiliary circle is equal to BB prime is to A prime. So that is proposition number 4 of works of Archimedes, specifically from on the conoids and spheroids. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.